Alrighty, welcome back to another lecture. In this section, we're going to talk about how to run hypothesis tests on more than two proportions. Okay, so if we're testing three or more, what kinds of tests can we run? And there are a couple different kinds of tests. One is called the goodness of fit, and the other is called the homogeneity of proportions test, or the test for independence. And we'll talk about that connection a little bit more later. But both of these tests are called a chi-squared test. So this is the Greek letter chi, right? So this is chi squared. So both of these tests are they follow a chi-squared distribution, and so consequently that's what we'll use to get the p-values for these tests. And so they're both called chi-squared tests. I want to do a couple examples of each of these tests, so let's get to it. For the goodness of fit, the goodness of fit test is used to determine whether the sample proportions that we've collected in our data match with some kind of hypothesized distribution. For example, suppose that we want to test whether bags of M&Ms contain 13% brown, 14% yellow, 13% red, and so forth, right? If we want to test whether that's the breakdown of the colors in the bag, then we would run a goodness of fit. Okay, our null hypothesis would be that, if we call the brown candies group 1 and the yellow candies group 2 and so forth, then the null hypothesis would be that P1 equals 13%, right, 0.13, and P2 equals 14%, 0.14, and P3 equals 13%, and P4 is 20%, and so forth, right? So that's how we would state the null hypothesis. Now, for the alternative hypothesis, we're just going to write this down in words, okay? So don't try to get fancy and write it down in math symbols, because there are actually lots of ways that the null hypothesis could fail to be true. For example, it might be the case that P1, P2, and P4 are equal to the values that are stated in the null hypothesis, but the rest of them are different. Or maybe it's P1, P3, P4, and P6 that are the same, but the other two are different. Or maybe they're all different from what's stated in the null, right? There are so many different ways that H null could fail to be true that we just can't write them all down. Well, we could, but it would take a long time. So it's better to just write it out in words, right? So in words, we'll just say at least one of the PIs is different than stated in the null. Or in other words, at least one of the proportions is different than the null hypothesis claims, okay? So we're going to test that null hypothesis by determining how well what we collected fits with the distribution posed in the null hypothesis. And some notation to get us started here. Little n, as usual, will represent the sample size. P sub I is going to represent the proportion of individuals with characteristic I. So, for example, here, P sub 1 was the number or the proportion of brown candies, right? And P2 was the proportion of yellow candies. E sub I is the number of individuals expected to have characteristic I. Now, we can calculate E sub I. We can calculate that expected value, right? If we know that there are n individuals in the sample and P sub I % of them have the characteristic, then the number of individuals with the characteristic would have to be n times P sub I, right? In other words, if you have a sample of 200 people and 20% of them have, whatever characteristic we're interested in, then the number of individuals expected to have that characteristic would be 20% of 200, right? N times P. Okay. O sub I is the number of individuals observed to have characteristic I. O sub I cannot be computed. Those are the data that we obtain, right? They're the data that we observe. And then finally, a lowercase k is going to represent the number of the number of proportions being tested. So in the M&M's example, we can see that k equals 6 because we're testing 6 proportions here, right? Okay. So here's how the goodness of fit test goes. We don't have a left-tailed, right-tailed, and two-tailed option here. It's always going to be, the hypotheses are always going to be stated this way, right? The null hypothesis is that P1 equals some claimed value, P2 equals some other claimed value, and so forth. And then the alternative is going to be that at least one of the proportions is different than stated in the null hypothesis. But then, everything else flows the same way, right? We'll look at the sample evidence, right? So in this case, since we're testing proportions, and in particular, since we're testing K proportions, we'll have K sample proportions that we'll want to compute. And then we'll compute the p-value in ArtofStat. Okay, so we'll go to ArtofStat and we'll navigate to the chi-squared test web app. Now, in that web app, there's going to be two options. There's going to be a goodness of fit option, and then there's going to be a homogeneity / independence option. If we want to run the goodness of fit, then obviously we need to make sure to choose the goodness of fit option. Okay. We'll enter the data that we were given into the contingency table, and then I'll kind of show you how to do the rest as we look at an example. As always, if our p-value is less than alpha, we reject the null. And if we're rejecting the null, that means there's evidence to support the alternative. There are conditions to check to run this test, as there are for any test that we would run, and these are the conditions. All of our expected values need to be more than 1, and at least 80% of the expected values need to be more than 5. So I haven't really emphasized the checking of conditions so far, because so far the conditions that we've had to check have been conditions we've checked in the past already. But these are a new set of conditions that we've never seen before. So I will show you how to check the conditions. Fortunately, it's really easy to do because ArtofStat will compute the expected values for us. We could do it ourselves if we wanted, right, by using this formula. But, if ArtofStat will do it automatically, then we might as well just let ArtofStat do it. And so then all we have to do is look at the expected values and make sure that they're all more than 1 and that at least 80% of them are more than 5, right? And if those conditions hold, then our test results are valid. So without further ado, let's look at an example. This first one's, that M&M's example, right? Mars Inc. claims that this is the breakdown of the colors in an M&M's bag. And we want to test to see if that's true. So we randomly select a bag of M&Ms and count the number of M&Ms in each color, and we get these results down here, okay? So part A says, at the 0.05 level of significance, can we conclude that the bag we purchased agrees with the manufacturer's claim? Well, let's see. The null hypothesis would be that, yes, it does, right? That the proportion of brown candies, and by the way, I'm just going to call this group 1, group 2, group 3, etc. Okay, so the null hypothesis would be that P1 equals 0.13, right? Because that was the proportion of brown candies that Mars claims. The proportion of yellow candies, P2, Mars claims that that's 14%. And for P3, they claim 13%, right? 13% red candies, 20% orange candies, 24% blue candies, and 16% are green candies. Okay, so there's our null hypothesis. The alternative hypothesis, we'll just write this in words. We'll say at least one proportion is different than stated in the null hypothesis, okay? So there's step 1. Now step 2 is to compute a bunch of sample proportions. To do that, we'll need to know the total number of M&Ms in our bag. We know that there are 17 M&Ms in the bag in total. That there are 17 brown M&Ms in the bag. But what we don't know is the total number of M&Ms in the bag. So I'm going to do a little bit of work here just to add up these numbers. So I'm going to give myself a total. And let's see. So we can type in 17 plus 20 plus 7, etc. into our calculator and see what we get. Okay, and that comes out to 72. So the proportion of brown candies in the bag would be 17 out of 72, which comes out to approximately 0.236. Okay, and then we'll do the same thing for the other colors. Okay, so there are all of our sample proportions for step 2. And what we can do is we can kind of start to look and see, okay, so for brown candies, we expected 13% of the candies to be brown, but what we actually saw was about 23.6% of the candies were brown. Okay, so that's quite a bit. That's quite a bit more than what we expected. And then on the other end of the spectrum, we expected 16% of the candies to be green, but only about 8% of them were. So, are we going to reject the null hypothesis? Well, that depends. Generally speaking, I think for a goodness of fit test, you need a fairly large sample size in order to get good evidence. And so I'm not sure that a sample size of 72 is really going to be good enough here, despite the fact that we're seeing pretty large differences between the claimed proportions and the actual observed proportions. But there's only one way to know, right? And it's to run the test. So we'll go ahead and get our p-value now. So we're going to go, to get our p-value, we're going to go to the chi-square test, and we're going to run the goodness of fit. Okay, so make sure to write those things down. And then otherwise, we're just going to enter the contingency table. So you can just say, entered contingency table. Okay, and I'll show you how to do that in a second. But then once you do all of that, you'll get a p-value. So let's head over to Art of Stat and do that. Okay, Art of Stat. I'll go to Web Apps. And the chi-square tests, I think, are going to be below these comparing to groups apps. I think they're going to be even further down. Yep, chi-squared tests down here. Okay, and I don't want the test for independence / homogeneity. I want the goodness of fit. Okay, and I'm not going to do an example from the textbook. I have my own contingency table that I'll put in. The first thing we'll need to do is put in the number of categories, because then it'll adjust how many columns the table has. So we'll change this to 6 since we have 6 colors. And if you want, you can change the names of the colors, although it's not totally necessary, but maybe I will. Brown. Okay, so you can change the colors. And then obviously you're going to put the observed counts where it says counts, and you're going to put the proportions from the null hypothesis in the proportions row. So for counts, we had 17. It doesn't like it when I use tab for some reason. 17, 20, 7, 9, 13, and 6. So I'm just copying that data over. Okay, and then for the proportions, we expected 13% brown. We expected 14% yellow. We expected 13% red, 20% orange, 24% blue, and 16% green. Okay, so once you've done all that, then you can hit submit, and it'll calculate the p-value for you. It'll also give you this little table up here, which is really nice. They restate the null hypothesis here in the second row, as well as the observed counts that you entered in, and so you can check your work there. Notice that the total was 72, just like we thought. They also give us the expected counts, so they don't give us the expected proportions, but they give us the expected counts. I'm sorry, they don't calculate the sample proportions, is what I meant to say. I wish that they did. I wish that they computed the sample proportions for us, but that's just the calculation we'll have to do by hand if we want to do it. But they do give us the expected counts, and this is important because when we talked about having to check conditions, we said our expected counts need to all be more than 1, which they are, and at least 80% of them need to be more than 5. Well, in this case, 100% of them are more than 5, right? 100% of these expected counts is more than 5, so we're good there as far as expected counts are concerned. Residuals we'll talk about in a moment. But the main thing we came here for is the p-value. So our p-value is 0.0005. So I was wrong. I guess you don't need a ton of evidence to reject the null hypothesis, because we only had a sample size of 72. But then again, the proportions were quite different, right? So let's write down our p-value, and then we'll write our decision and our conclusion. Okay, so we need to compare our p-value to our level of significance alpha. And we want to know if this statement is true, right? Is our p-value less than alpha? And in this case, yes, it is, right? 0.0005 is less than 0.05. So we reject H null. Okay, since we're rejecting H null, we have sufficient evidence to support the alternative, right? At least one of the proportions is different. And we should state that we should refer back to the actual scenario in question here. The scenario is whether or not these colors in our bag match the distribution that Mars claims there should be in the bag. And what we're finding out is that no, actually it doesn't, right? We have evidence to suggest it doesn't. So we'll say something along those lines. Okay, so there is sufficient evidence to conclude that the color distribution in our bag is different than the distribution claimed by Mars Inc. I should say than, not that. Okay, very good. So now part B says, what do you think the residual measures? Which color had the largest residual? Comment on how the distribution in our bag differs from the color distribution claimed by Mars, because we discovered in part A that our bag is different, right? Is different. So, but how is it different, right? So let's look at Art of Stat again. Okay, so it's saying that it disconnected from the server. If I reload, I'm gonna have to redo the whole problem. But fortunately, we can still kind of see beneath the gray what's going on. So the residuals are this bottom row in the table that Art of Stat computes for us. And what the residuals measure, if you look at this, this difference, this number 7.64 is the difference between what we expected here and what we observed, right? It is a little bit strange that they round the residuals to 2 decimal places, but they only round the expected values to 1 decimal place. And so maybe that is kind of throwing you off a little bit. But if you subtract 17 minus 9.4, you get 7.6, right? And if you do 20 minus 10.1, you get 9.9. And if you do 7 minus 9.4, you get negative 2.4, and so forth. So that's what these residuals are. It's the difference between what was expected and what was observed. When we have a positive residual, like in the case of the brown candies, then that means that we observed more brown candies than expected. And when we get a negative residual, that indicates that we observed fewer, in this case, orange candies than we expected. Okay? But the magnitude of the residual kind of shows you how different things are. The largest residual, of course, is yellow. They're almost, we had almost 10 more candies than we expected to have in our bag. 10 more yellow candies than we expected to have in our bag. That's a substantial amount. So how does our bag differ from Mars's claims? Well, I would say there are more yellow and brown candies than Mars claims, and fewer of all the other kinds of candies. Red was pretty close. You're never going to have a residual that's exactly 0, right? Most of the time it's going to be off by at least a little bit. But red is pretty close. But I would say there are more brown and yellows and fewer orange, blues, and greens than what we expected. Okay, so something like that. So our bag has more browns and yellows and fewer oranges, blues, and greens. Than expected. Reds were approximately, reds were about right, okay? But the rest of them, yeah, there were some pretty significant differences. So anyway, so that's it for part B. Well, I guess we didn't really answer the first question though, right? What do you think the residual measures? We said it in words, but we didn't write it down. I don't think I am going to write it down, but let me just reiterate it again, and maybe you can write it down in your notes, right? But what do you think the residual measures? The residual is the difference between what we observed and what we expected. It's observed minus expected. Okay, residual equals observed minus expected. Which color had the largest residual? That was brown, right? Brown, or no, I'm sorry, it was yellow. Yellow had the largest residual. It had a residual of 10. Okay, moving on. Here's another example. An urban economist wishes to determine whether the distribution of residents in the United States is the same today as it was in 2000. He randomly selects 1,500 households in the United States and finds the distribution in the table below. Test the claim that the distribution is different today than it was in 2000 at the 0.05 level of significance. Okay, so these are the data that the researcher observed, and these were the proportions back in the year 2000. So I will let you pause the video and see if you can write down the hypotheses for this test. Okay, so here's my solution. If we call the Northeast Group 1, the Midwest Group 2, the South Group 3, and the West Group 4, then we should have these proportions for our null hypothesis. Okay, notice that I'm just taking these percentages and converting them to decimals by moving the decimal 2 times, right? 2 times to the left in each case. Okay, and then the alternative is that at least one of those proportions is different than claimed in the null hypothesis. So for step 2 then, we'll have 4 sample proportions to compute. I will let you go ahead and pause the video and do that. Okay, so here's what you should have for those sample proportions. First of all, you would have to compute the total, except that in this case, the total was given to us, right? 1,500. But if you add up these numbers, you do indeed get 1,500. And then you're going to divide each of these numbers by that total to get those sample proportions. Okay, next thing we want to do is compute the p-value. So once again, I'm going to let you pause the video and see if you can do that on your own. Okay, so of course we're going to want to come to the chi-squared test. We want to run a goodness of fit test, so make sure you select that. I have my own contingency table, and this time I do happen to have exactly 4 categories. Okay, so that's good. Optionally, you could change the names of the categories if you want. You don't have to, but I'm going to go ahead and do that. And then you're going to want to put the counts and the proportions in their appropriate places. Notice that this table has the second and third rows in the wrong order. In other words, in the notes, we had the percent in 2000 in the second row, and then the observed counts in the bottom row. But here it's mismatched, right? So the count for people in the I said northwest, but it should be northeast. But the count for the people living in the Northeast was 299, not 19%, right? 19% was the expected proportion, so that should be 0.19, okay? So just make sure you don't get those rows, or rather, you make sure that you put the bottom row in the notes in the middle of this. Just pay attention is what I'm trying to say, right? Like where you're asked to put the counts, and where you're asked to put the proportions, put the proportions. Okay, so this is what it should look like once you get everything in there. Click submit, and then you get your p-value. This is really interesting. Looking at the residuals, for example, here we have a residual of 14, which was bigger than any of the residuals we saw with our M&M's example. However, in this example, we had a sample size of 1,500, whereas in the M&M's example, we only had a sample size of 72. So in the M&M's example, to see a residual of 10 was a lot, okay, because there were only 72 candies to begin with. But when we have a sample size of 1,500, a residual of 14 is actually not that much, which is why we're getting such a large p-value. We're saying, yeah, there's not really good evidence to say that the proportions are different than what is stated in the null hypothesis, right? It's very likely that we would get the results that we obtained if the null hypothesis were true. So anyway, we can write down that p-value, 0.7174. Okay, so then for the decision and conclusion, 0.7174 is our p-value. Our level of significance is 0.05. We want to know if our p-value is less than alpha. It's not in this case. So do not reject H null. Okay. And then we can go ahead and write down a conclusion. There's not sufficient evidence to say that the distribution is different today than it was in 2000. Okay, the distribution of what? Of residents in the United States. Okay. Okay, so there's not sufficient evidence to conclude that the distribution of U.S. residents is different today than it was in 2000. I'm sure we have some follow-up questions. Part B, what does the p-value mean in this situation or in this scenario? Well, the p-value is, let me change colors. The p-value is the probability of obtaining the sample statistics that we obtained if the null hypothesis were true. That's a pretty large p-value, right? It's a pretty good probability. There's like almost a 72% chance that we would obtain these results if the null hypothesis were true. So there's absolutely no reason whatsoever to reject the null hypothesis. So we don't do it, right? We don't reject the null. Okay. It means there is a 71.74% chance of obtaining the sample proportions that we obtained if the null hypothesis were true. And I suppose I should be honest with you here and say that I'm being somewhat glib. This isn't, the exact meaning of the p-value. The exact kind of mathematical meaning of the p-value here would be somewhat involved to work out. But loosely speaking, right? Loosely speaking, this is what the p-value is telling us, right? It's telling us that there's about a 71.74% chance of obtaining sample proportions like the ones we obtained if the null hypothesis were true, which of course a 71.74% chance is a really good chance, right? So it means, well, there's no reason to suspect the null hypothesis of not being true. Okay, part C. According to the results of this study, has there been a statistically significant change in the distribution of U.S. residents since the year 2000? Well, pause the video. The answer is no. No, because we did not reject H null. This is important because if I asked you a follow-up question like, how has the distribution changed? Or like, something along those lines, your answer really should be, well, the distribution hasn't changed. There's not sufficient evidence to say that the distribution has changed at all, right? So no, we don't have statistically significant evidence here. Moving on. Let's talk about a different test, the homogeneity test. So the homogeneity of proportions test determines whether the proportions of subjects in various groups who have some characteristic are homogeneous, or in other words, the same. Okay, for example, Zocor is meant to lower cholesterol. Researchers were interested in determining what side effects it causes. Group 1 received Zocor, Group 2 received a placebo, and Group 3 received cholestyramine. Is the rate of abdominal pain the same in each group? Well, to answer that question, we could run a homogeneity test. The null hypothesis would be that, yes, the abdominal pain rate, or the rate of abdominal pain, is the same, right, in each group. P1 equals P2 equals P3. The alternative would be that at least one of those proportions is different from the others. Now, once again, we're just going to state our alternative hypothesis in words, like we did for the goodness of fit test, because there are multiple ways that the null hypothesis could fail to be true. It could be that P1, P2, and P3 are all distinct from each other, or it could be P1 and P2 are the same, but P3 is different, right? Or it could be that P2 and P3 are the same, but P1 is different. Or it could be that P1 and P3 are the same, P2 is different, right? So there are a whole bunch of ways that H null could fail. So rather than writing down each individual way, we just say, well, the alternative is going to be that at least one of the proportions is different from the others, okay? Now, to run this test, we're going to arrange the data into a contingency table. Most of the time, that table will be given to you. And most of the time, the table will only consist of this portion of it. It probably won't give you the totals, but ArtofStat will compute those totals for us. So this table we would call a 2x3 because there are 2 rows and 3 columns, right? 3 columns. So let me relabel this: 2 rows. 2 rows and 3 columns, so it's a 2x3 table. Okay, so I'm just pointing that out to you because it might help with some analysis a little bit later on. Okay, the notation for this test is the same as the notation for the goodness of fit. Okay, with a couple of slight modifications. E is still going to represent the expected value, but we'll use 2 subscripts now, E sub ij, because this is going to be the number of people expected to be in the ith row and the jth column, right? So like the first row, second column would be this thing right here. And the second row, first column would be this thing right here, right? So because this table is like a 2-dimensional thing, we have to have 2 subscripts to describe, each of these little locations. So that's not something you'll have to worry a ton about. Like, you're not going to get something wrong because you couldn't figure out what E sub 3,4 was, but anyway, that's why we have the notation the way we do. So E sub ij, these are the expected values. O sub ij are the observed values, right? They're what we actually observe in the table itself. And then once again, K is the number of proportions being tested. In the Zocor example, K would equal 3 because we're testing 3 proportions here. Okay, we've got 3 columns. One thing that deserves a little bit of discussion is how to compute the sample proportions. This is this can be a little bit tricky for a homogeneity test, and we'll describe why in a second. But for now, I'll just say, suffice it to say, there's a lot about the homogeneity test that we're not going to fully explore until we talk about independence in Unit 4. Okay, so we will come back to this test in Unit 4 when we've had a chance to discuss the concept of independence. But for now, if you have a table with 2 rows, like this table up here, the sample proportions are usually going to be the entry in the top row of column I divided by the column I total. In other words, if you want the sample proportion of Zocor patients who experienced abdominal pain, you would take the number of Zocor patients who experienced abdominal pain and then divide by the total number of Zocor patients. Okay, and if you wanted the proportion of placebo patients who experienced abdominal pain, you would take the number of placebo patients who experienced abdominal pain and divide by the total number of placebo patients, right? So that's what this formula is trying to point out to you. Okay, here's the test. And we're going to get the p-value from the same place, the chi-squared test app. The difference is that we're going to choose test of independence / homogeneity instead of goodness of fit. Okay. Okay, so a couple other things to say, and then we'll look at some examples. So first bullet point here says, for reasons that we're not going to get into, this is how we compute the E sub ij's, the expected values, right? The O sub ij's are not, they're not computed, those are observed, but the E sub ij's can be computed, and this is how we do so. And again, I'm not going to get into a ton of detail as to why that is the case. The good news is that ArtofStat will compute these values for us, and that's important because we have to have those expected values in order to check conditions, okay? So, without further ado, let's finish up that Zocor example. So here are the numbers that we obtained from the Zocor example. We want to compare the Zocor patients to the placebo patients to the cholestyramine patients, right? P1, P2, P3. Is there evidence that the proportion of subjects in each group who experienced abdominal pain is different? Well, the null hypothesis would be that no, they're not different, they're the same. The proportion of ab pain is the same in all three groups. Okay, the alternative hypothesis is that at least one proportion is different from the others, or from the rest, or whatever you want to say. Okay, step 2 is to compute those sample proportions, right? So for P1 hat, we're going to want to take the number of Zocor patients who experienced abdominal pain, and we're going to divide that by the total number of Zocor patients. Now, I'm not sure if that information was given to us in the problem, so we'll have to just make a little total row and figure that out ourselves. Okay. So if we add 51 plus 1532, I'm just going to do this in my head, 1583, I believe. So we'll do 1583. Okay. For the placebo patients, it was 157. And for the cholestyramine patients, 179. So those are the totals there. Anyway, we can punch these into our calculator and see how much they are. So these are the sample proportions we should end up with when we punch all of that stuff into our calculators. Notice I'm getting the numerators from the numbers of people in each group who had abdominal pain, right? So I'm getting them from the abdominal pain row. Looking at those sample proportions, I would say, like, just comparing Zocor and cholestyramine to 3 decimal places, these are not different at all. They're exactly the same. Okay, Zocor to placebo. Zocor to placebo. They have the same proportion, right? It's the cholestyramine that looks like it's different. Okay, now is that a statistically significant difference? Well, there's only one way to know, right? And that's to go ahead and run the test. So we're going to go to the chi-square test. And this time we're not going to run a goodness of fit. We're going to run a test for homogeneity. But we are going to enter the contingency table again. So entered table. And I'll show you how to do that. Okay, we'll go over to ArtofStat and do that together. But it'll spit out a nice p-value for us. And then we'll be able to make a decision and write out a conclusion. So let's go over to ArtofStat. Okay, so I'm going to open up that same chi-squared test app. And this time I want the test of independence / homogeneity, so it's already set up to run that test, which is good. So to set it up, notice that, well, first of all, let's not do the example from the textbook. Let's go ahead and go over to contingency table. What we can do is notice that these labels, these category labels above average, average, below average, those are listed in these rows here. So I'm going to want to change that to abdominal pain and no abdominal pain. And we can just put a comma between them. So ab pain, no ab pain. And then you see that it's making the table as we go, which is pretty nice, right? So ab pain, no ab pain. It's also going to compute all the totals for us, which is pretty nice. For the column labels here, we don't want not happy, pretty happy, and very happy. What we want is Zocor, and then put a comma, placebo, and then put a comma, and then cholestyramine. Okay. So now this table is starting to take form. It's starting to look a little bit more like what we had on our notes. To fill in these numbers here, I actually have to fill it into this table down here. So I'm going to click on the Zocor box and put in 51. Okay, 51. And then for the placebo, 5. And then for the cholestyramine, 16. That's for the ab pain row. And then the same thing for the no ab pain row, 152. And cholestyramine, 163. Whoops, 163. Okay, and then you just hit enter, and Art of Stat will think about it a little bit, but then it'll go ahead and compute stuff. It's really nice. It gives us this kind of side-by-side bar chart so you can compare the distributions, so that's kind of cool. What else are we given? We're given all these totals, okay, which is nice. Here we're given these aren't the expected counts. I'm sorry. Actually, I'm not sure we want the conditional distribution at all. We definitely want the expected counts, though. Okay, because the expected counts, what we need to do is we need to look at these numbers and we need to make sure that they're all more than 1, which they are. And then we also need to make sure that at least 80% of them are more than 5. And they're all more than 5, so I think we're good, right? We're good to go ahead and run the test, right? The results of the test will be legitimate. If we want to know what the residuals are, we can click on this little box to show the residuals. And again, it's even telling you here, the residuals are observed minus expected. So it's telling you that for Zocor patients, we observed 8 fewer patients than what we expected having ab pain. For the placebo group, it was basically spot on. And then for the cholestyramine group, we observed that 9 patients more than what we expected ended up having abdominal pain. So anyway, this is good enough for us to reject the null hypothesis. We get a very small p-value, 0.0006. So let's write that down. Okay, 0.0006 is less than 0.05, so reject H null. Since we're rejecting the null hypothesis, that means there's evidence to support the alternative, right? At least one of the proportions is different from the others, right? So is there evidence that the proportion of subjects in each group who experienced abdominal pain is different? Yeah, what we would say is there is sufficient evidence to conclude that at least one of the treatments, or maybe we'll say at least one of the treatment groups, experienced a different rate of abdominal pain than the others. Okay, so at least one of the groups experienced a different rate of abdominal pain than the others. Now, the test itself does not tell us which group is different, right? For us to determine which group is different, we have to look back at step 2 and say that, oh, it's probably cholestyramine, right? the Zocor and placebo patients had pretty much the same rate of abdominal pain, but cholestyramine patients had an elevated abdominal pain. Okay, again, the test itself doesn't tell us that. We have to look back at step 2 to figure that out. Okay, so part B asks, are the results of this test good news or bad news for Zocor? And I would say the results are good news. The results here are good news. Since Zocor patients had about the same rate of ab pain as the placebo patients. In other words, the patients who didn't even take any real medication. So Zocor patients have about the same rate of ab pain as the placebo patients, and significantly less ab pain than the cholestyramine patients. So that basically that means that Zocor is not causing abdominal pain, right? Which is good news for Zocor. The purpose of the medication was to decrease cholesterol. If it's effective at doing that without causing abdominal pain, then it's a superior drug to cholestyramine, which is good news from Zocor's perspective, right? Okay. An equivalent way to view the last example is in terms of independence. This is not something I'm going to dig into a ton right now, but we will come back to this topic in Unit 4. But to see why those things are equivalent, notice that if there's no difference in the proportion of patients who experienced abdominal pain between the medications, then the variables abdominal pain and medication are independent. In other words, if whether or not you experience abdominal pain, if the medication that you take doesn't affect the likelihood of you experiencing abdominal pain, then the variables abdominal pain and medication are independent, right? So anyway, if there is a difference in the proportions of patients, like we saw, for example, that cholestyramine patients had a larger proportion of abdominal pain, then obviously whether or not you experience abdominal pain depends on the medication you took, right? So that's why the test is called a test for independence / homogeneity. We're thinking of it as a homogeneity test for right now, but it could also be thought of as a test for independence, and that's a topic that we'll discuss in Unit 4. In order to interpret the results of the test correctly, we should be a little bit more careful about the way we state our hypotheses. For now, we're just going to state our hypotheses like we have been doing. But in Unit 4, we'll come back to this idea, and we'll be a little bit more careful about the way we're stating our hypotheses. Okay, so just FYI, like for your information, we're going to be more careful about this in the future. But for right now, we'll just continue kind of doing stuff the way that we have been. So let me give you one last example. In a study of 1,358 randomly selected deaths of men aged 45 to 64, the victims' smoking habits, along with whether the individual died of cancer, are listed. Part A asks, are the proportions of cancer deaths the same in each smoking category? Test at 0.01. Okay. I will let you pause the video and write down the hypotheses. Okay, here's what you should have, right? So we're going to compare 4 proportions here. The proportion of non-smokers who died of cancer, the proportion of mild smokers who died of cancer, the proportion of moderate smokers who died of cancer, and the proportion of chain smokers who died of cancer. I'm calling those groups 1, 2, 3, and 4 respectively. And so the null hypothesis would be that, well, there's no difference between these groups. They all have the same rate of cancer deaths, right? P1 equals P2 equals P3 equals P4. The alternative would be that, no, at least one of the groups is going to have a different rate of cancer death than the others, right? At least one PI is different from the others. Step 2 then would be to calculate the sample proportions. And so once again, I'll let you give the video a pause and see if you can calculate those sample proportions. Okay, here's what you should have for step 2, right? These are the sample proportions. Again, you just need to total each of the columns, and then the proportion of cancer deaths among non-smokers would be the number of cancer deaths among non-smokers divided by the number of non-smokers, right? So 55 over 360 is 0.153. 52 out of 350, 0.149. 88 out of 313, 0.281. And 135 out of 335, 0.403. Just looking at those numbers, do you notice how they increase? I mean, I guess there's a slight decrease from group 1 to group 2, but then a huge increase from group 2 to group 3, and then an even bigger increase from group 3 to group 4. So I would guess that we're going to reject the null hypothesis. It seems like the more you smoke, the more likely you are to die of cancer, which is not surprising, right? But only one way to know for sure, of course, and that's to run the test. So let's compute the p-value. Okay, so we're back here in the chi-squared test, and we do indeed want to run a test for homogeneity, so we'll leave that. I have my own contingency table to enter, and let's fix the labels. So for my row labels, I want died of cancer and did not die of cancer. Okay, for my column labels, I want non-smoker, mild smoker, moderate smoker, and chain smoker. Okay, and then down here I can enter my values, 55, 52, 88, 135, 305, okay. So you enter all those values and hit enter. Make sure that they're entered correctly up here. You get all of those totals, which is nice. And they give you some a conditional distribution here. I think more helpful is looking at the expected counts and also the residuals. So for the expected counts, yeah, all of these are more than 5. All of them are more than 1. So we're good. The results of our test are valid. Looking at the residuals, for non-smokers, we had 32 fewer cancer deaths than expected. Same for mild smokers. So for non-smokers, 32 fewer. For mild smokers, 33 fewer. For moderate smokers, we had like 12 cancer deaths more than expected. And for chain smokers, we had like 54 more cancer deaths than expected, if in fact they were the same. Looking at these bar charts, I think this is interesting. So green is non-smoker, yellow mild smoker, blue is moderate smoker, and red is chain smoker. And you can just see how the proportions increase as your smoking habits increase as well. So anyway, very small p-value here. It's saying less than 0.0001. Here it just says 0. The reason it's saying that is just because the p-value is so small that there aren't enough digits to store it, right? It's whatever it is, it's less than 0.0001. And that's enough for us to reject the null hypothesis easily, right? 0.0001 is less than 0.01, so reject. Yep. So yes, there's sufficient evidence to conclude that the proportion of cancer deaths is not the same in each category, right? The proportion of cancer deaths is different in at least one of the smoking categories. Okay, so there's our conclusion. Now, once again, we don't know which category is different, or maybe it's more than one. Like maybe all four of them are different from each other. We don't know. The test doesn't tell us. All the test tells us is that at least one of them is different from the rest. Okay. So now part B asks us to describe the relationship between smoking habits and cancer deaths. Now, if we had not rejected the null hypothesis, we would say there is no relationship between smoking habits and cancer deaths, right? But we did reject the null hypothesis, which means that at least one of the proportions is different, so there must be a relationship between smoking habits and cancer deaths. So now to answer the question, to describe that relationship, we would just look back at step 2, of course, and we would notice what we've been noticing all along, which is that the proportion of cancer deaths increases the more you smoke, right? And that's what we would say. Okay, so the risk of cancer death seems to increase the more you smoke. Okay, this last page is just a summary of the different proportion tests that we've covered in this unit. So way back at the beginning of chapter 3, we talked about the one sample proportion test. We spent some time talking about that test, but also talking about confidence intervals and stuff like that. But so we have the one sample proportion test, and then we introduced the two sample proportion test. And now in this section, we've done the goodness of fit and homogeneity tests. Just to kind of compare and contrast these, right? Obviously, if you only had one sample, one group, then you would run the one sample test. If you had two groups, then you run the two sample test. If you have more than two groups, then you have to decide between either the goodness of fit or the homogeneity. And to help you do that, notice that in the goodness of fit test, the null hypothesis is that P1 equals some value and P2 equals some other value. Whereas in the homogeneity test, we don't have any claimed values. We just want to know if the proportions are equal to each other. Okay, so that's one kind of dead giveaway between those two different kinds of tests. Another thing that I'll point out to you is that the goodness of fit test is really kind of it's just an extension of the one sample proportion test, right? Because it says P1 equals some value, just like the one sample proportion test P says P equals some value, right? The difference is that for the goodness of fit test, you have multiple proportions that you're testing simultaneously, right? In the same way, I would point out that the homogeneity test is an extension of the two sample proportion test, because instead of saying P equals some value, it just says P1 equals P2, okay? And the homogeneity test is saying the same thing, except it has more than two proportions, right? So that's another kind of connection that you can see between these different tests. What else did I want to say here? Okay, this last bullet point down here. This might cause you to scratch your head a little bit for now, but again, it's something we'll come back to in Unit 4 when we talk about independence. But the idea is that the goodness of fit, the reason for the goodness of fit is to explore more than two proportions that come from one population, okay, from one population, okay? Whereas the reason for the homogeneity test is to explore more than two proportions that come from more than one population, okay? So goodness of fit, the values come from one population. For a homogeneity test, the values come from more than one population. Okay, so just to give you some examples of that, right? If we wanted to know whether the proportions of candy colors in a bag of M&Ms are equal, we would run a goodness of fit test, right? We would just, because we only have one bag of M&Ms that's coming from one population, but we have multiple colors, right? We have like 3 colors, so we would have like 6 colors, right? So we would be testing 6 proportions, but they all come from one bag, one population. So we would run a goodness of fit there. But if we want to know whether the proportions of candy colors in one bag of M&Ms match the proportions of candy colors in another bag, that's when we would run a homogeneity test, because then we would have 2 separate bags, right? 2 separate populations. So anyway, we'll consider this in a little more detail when we discuss fully the connection between homogeneity and independence in Unit 4. But for now, hopefully that's helpful. when you're trying to decide which test to run in which scenario. So that'll do it for this section, and I will check in with you in the next one.